Swayam Prabha. Digital India. Educated India.
Plan in this lecture is just to follow up on the previous lecture on shortest paths, and we are going to look at a more general problem, that is computing the shortest paths in a graph where you want to compute the shortest paths between all pairs of vertices, right. So, here earlier in the morning we looked at the single source shortest paths algorithm, that is we are given. So, we will set up our input very clearly. We have a graph G, which is, we will work with directed graphs for this lecture. All these things can be applied for undirected graphs, but for the purpose of showing things clearly we will look at directed graphs. And as usual, for every edge we have a weight of the edge WE, which we will assume that it's a positive real number. Again, you can think of it for now as positive integers, but this again works for positive reals. And as has been mentioned in the previous lecture, that if you have negative weight cycles, shortest paths are not even defined. When you have negative weight edges but no negative weight cycles, shortest paths are well defined and can be computed, but Dijkstra's algorithm does not compute them correctly. There is a small thing that works when, if you have all the negative edge weights which are all the negative edge weights that are there in the graph are incident only on the source vertex S from which you are starting the single source shortest path, then Dijkstra's algorithm continues to work, and you can verify this. All the other edges that are present in the graph must be non-negative. They can be either positive or zero weight. Under such circumstances, Dijkstra's algorithm still works, but we will assume for this lecture that the edge weights on this graph, edge weights are always non-negative, right. And what is our goal? We are interested in outputting a matrix which we will call as the all pair shortest paths matrix. So, what does this matrix contain? For a pair ij, it contains the shortest path distance from I to j. Because the graph is directed, we will talk about distances from a vertex to another vertex. And also one would like to know what is a shortest path, right. There can be multiple shortest paths, but at least one candidate path should be output. So, this is also relevant in the single source shortest path setting, but here let us ask, we just want to suppose at the end of the algorithm if you output this distance matrix, it just tells you the distance between from I to j, but you would also like to know, give me a shortest path. How would you store such a representation of the shortest path? One way is to explicitly store all shortest paths, right, but remember that there are n squared pairs for which we are trying to output the distance, and each path, how long can it be in the worst case? Long only in terms of the number of edges, because the distance is already stored, but if you have to represent the path as the actual edges on the path or the intermediate vertices, what is the storage requirement for such a representation? Sorry? Yes. What for a single path, how much space do you require? N, theta of n, because there can be some paths which are of the form V1, V2 up all the way. If it is from V1 to Vn, it could be containing all the vertices or theta n vertices on that path. So, therefore, if you explicitly store all paths, your output representation is going to be huge. So, therefore, is there a better succinct representation? Even in the single source shortest path, you do not output this for from S to every other vertex, you do not actually output the actual paths. How do you output the representation of the paths? So, maybe you recall that there is something called as a previous in the shortest path tree, right. So, we will make it a little more clear here. We will say that for every vertex, for every pair, let us say x to y, we know the shortest path distance by going through to the matrix, but we also want to know the shortest path, actual shortest path. So, we will store the first edge on the shortest path on the shortest path that we have computed from x to y, right. Now let's say that the first edge was xa, right, that was the first edge, and then the path goes all the way and goes to y. But then how do we actually construct this path from a to y? We do not know this path, right? Very good. So now this is recursive. We now know that we have not stored it only for x to y, we have stored it for every pair. So that when you go from x to a, this is the first edge. Now you must take a shortest path from a to y because of the substructure property that was discussed earlier. The shortest path from a to y must, the path from a to y must also be shortest. So maybe you have to, so you will have to look at the first edge from a to y and then say that xa, and maybe there is b on the first edge is ab, and then you go from b to y, and as you keep doing this, you have actually constructed the shortest path, right. So what have we done? Then we can also keep another matrix which is of order n squared size again, because it just stores one vertex or the edge, right, the first edge on the path, and that is sufficient for you to construct the path. So whenever somebody asks you, give me that path, you will spend theta of n time in the worst case, or theta of the length of the path for that path, right, between x and y. So this is the representation that we want as the output, okay. And so from the previous discussion, we already know that there is a very simple way of computing all pair shortest paths under this setting where the graph is, we are working with directed graphs, where the graph is directed and the edge weights are positive. You simply execute Dijkstra's algorithm repeatedly from all the sources, and you can think of each execution filling up one row of this matrix and one row of the other matrix also, the paths matrix also, right. So it's fairly easy, and one can do this in time, which I will say as n times execution of Dijkstra's algorithm. And I leave this unspecified because Dijkstra's algorithm can be implemented using various data structures. If Dijkstra's algorithm is implemented using simple arrays, you get an order n squared running time for Dijkstra's algorithm using arrays. If you implement it using binary heaps, you get a running time which is m plus n times log n using simple binary heaps. And if you do a little more sophisticated data structures, then you can get m plus n log n, right, using what are called as Fibonacci heaps, but this should not bother you. So we get a running time which is n executions of Dijkstra's algorithms, and we will, for the sake of this presentation, we will assume that, so I hope everybody is aware of binary heaps. Are there people who are not familiar with priority queues or binary heaps? Please raise your hands. So I'll assume that everybody knows what is a heap, the heap data structure, and what it supports. We'll just look at it, and we'll also write down the exact running time complexity, and therefore we are going to focus on this running time, and we will say that, okay, if I had a standard binary heap, I would get n times m plus n log n as the running time of the all pair shortest paths algorithm, which is a black box invocation of the Dijkstra's algorithm n times, right. So we would like to see whether there are better algorithms, and there is one such a different algorithm which uses some very nice ideas, and which is called as the hidden paths algorithm. And the reason to pick up and select this algorithm for this presentation is, one, it is a very clever algorithm which makes use only of the Dijkstra's algorithms and the ideas behind it. It doesn't require any sophisticated data structures. It introduces the idea of what is called as an amortized analysis, which very gently, and the final thing is that you will never possibly see this algorithm in your coursework. You will see other all pair shortest paths algorithms like Floyd-Warsaw and others, but this algorithm is possibly slightly out of the way, and hopefully it will show you some different things which will not typically get done in a course, right. Okay, so let us see what what all this algorithm uses. So the first thing that we are going to define is what we'll call as an optimal edge. So we know that we have the graph GVE, and we have always been using the terms n for the number of vertices, m for the number of edges, m for the number of edges. Now let us take an edge and ask when is it an optimal edge. So if it is an edge xy, I will call it an optimal edge if actually the weight on the edge xy, remember that is a weight of for every edge, is equal to the shortest path distance from x to y. Right? Clearly we don't know this ahead of time. This is what we want to find, what is d of xy. If you find this matrix, you know it at the end of the algorithm, you will know it at the end of the algorithm, is this edge an optimal edge. But we will call such edges as optimal edges, right? And now one can clearly see, and I will denote the set E star is equal to the set of optimal edges. And just by the definition, E star is a subset of E, and therefore we know that we will call also the cardinality of E star is equal to M star, just denoting, I mean taking clue from the E star, and we will call M star as the number of edges which are optimal edges. So therefore we know that M star is typically less than M. It could also be M, but it could be also significantly less than M, because there may be very few edges which are optimal edges. So that we understand this notion of E star, let us see, is there an example graph where E star is equal to E, that is every edge is optimal. Okay, so why do you say that it is in a tree? Okay, so in the tree, what is, I mean, is there between every pair, actually there can be either a path or there need not be a path. You are considering a directed tree, I assume, right? Okay, so now there is a unique path between every pair, and that is exactly the shortest path, because there is no other path, and therefore all the edges lie on the shortest path, right? Now similarly, this is already a sparse graph, that is tree itself has few edges, I mean it has n-1 edges, so it is already a sparse graph. And another example is that you can have a very dense graph, but it could be so under the case where all edge weights are the same, you can have actually every edge is an optimal edge, right? So if all the edge weights have the same value, then if you take any edge, or if it is an unweighted graph where you can think of it as a unit edge weighted graph, let us ask this question. So let's say this is the pair xy. What is the shortest path from x to y? It is the edge itself, because as soon as you take a path with multiple edges, you have a path which has weight, which is whatever is the weight on the every edge times the number of edges, right? Therefore every edge is in fact an optimal edge. Therefore you have examples where this M star can actually be equal to M, and therefore this M star need not always be smaller, but in several graphs one can expect that M star need not be equal to M, and M star can be significantly smaller than M, right? Any questions about the set E star? So we do not know what is this set E star when we begin our algorithm, but the goal of this hidden paths algorithm is to come up with a all pair shortest paths algorithm which runs in time, which is, so I will recall Dijkstra's based APSP, and so this APSP term is all pair shortest paths, and I will recall the complexity. We said that it is n times m plus n log n, right? So I will write this term as mn plus n squared times log n. This is the running time of Dijkstra's algorithm based all pair shortest paths algorithm. What we are aiming towards is an algorithm which is m star n plus n squared log n, right? So we may be better in some cases, we may be equal in case of Dijkstra, but we are no worse, right, in terms of the running time. Is this clear? This is the goal of this lecture. We are going to present an algorithm which runs in m star n plus n squared log n. So this is the saving that we do instead of mn plus n squared log n. Okay. So now let us view the shortest path, any shortest path from x to y between actually any pair x and y. And let us view this shortest path. We know that because of the optimal substructure property of the shortest paths, we have already seen that if you take any pair A, B in this on this shortest path, actually the shortest path from A to B is contained inside this path, right? There cannot be a shorter path. There can be other paths which are of equal weight, but there cannot be a strictly shorter path from A to B. Otherwise, you could have obtained a better path. So in terms of the edges now, so let's look at this path again, and every edge, so I will now label every vertex on this path, so I will call it A1, A2, A3, A4. I pick up any edge on this. What can you say about this edge? It must belong to E star. In fact, because of the same argument that if you take any pair, the pair is now just the endpoints of that edge. So every edge is belonging to E star. So intuitively what this algorithm tries to say is that Dijkstra's algorithm was taking a shortest path and trying to relax all the edges incident from on that vertex or outgoing from that vertex and make estimates about the tentative distance. So let's say this was S, this was U, then it is going to make estimates for V1, V2, V3. This algorithm says that if you somehow knew that some of them are optimal edges and some of them are not optimal edges, you better choose only optimal edges, because anyway whatever shortest paths you are going to get are going to be along only optimal edges, right? So this is the key intuition, but it is difficult to encode it because nobody knows what are optimal edges. That is the whole purpose of this algorithm, right? So that is the intuitive reasoning behind it. But let us ask ourselves, is there one optimal edge that we can identify very easily? Edge with the smallest weight. So let's do the following: scan all the edges in the graph. There are m edges in the graph, and order these edges according to their weight. So it takes m log m time to actually sort these edges according to the weight. Pick the edge which is the shortest edge weight. Now the claim is that if AB is the shortest weight edge from A to B, then this edge must be an optimal edge. This should be the shortest path from A to B. This should be quite obvious, right? Because there is no negative edge weights in the graph. Therefore, you cannot add up two edges and get a path which has weight which is strictly smaller than the weight of any edge. And this is important, that there are no negative edge weights in the graph. So therefore, under the assumption that we are working with non-negative edge weighted graphs, the edge with the smallest edge, the smallest edge weighted edge is certainly going to be an optimal edge. Very good. So at least we have a starting point. We know that we have identified one optimal edge, and we want to use this and keep doing something to get paths, longer and longer paths, right? So the idea is, the idea of this algorithm is based on the fact that the paths that you get, again very much like Dijkstra's algorithm, is going to be by taking a shortest path and extending it along an edge, right? That is how Dijkstra's algorithm or any algorithm is going to find paths, and this algorithm is also going to do the same thing. But remember that, I mean, if we had run n executions of Dijkstra's, we would have maintained n different heaps, right, which are corresponding to the single source shortest path starting at S, V1, V2, V3 up to Vn, and each of these heaps keep doing their work independently, right, and they do not share any information about them, and that is why we are not using something that some other heap or some other shortest path computation is finding out. So the idea here is that, can we reuse information about the shortest paths computation of the other executions which are happening for the Dijkstra's algorithm? That is, if you had spawned out n heaps, you would have certainly done what we wanted, but maybe there is a way to reuse and share information, right? So instead of maintaining n heaps that a Dijkstra's algorithm executed n times would maintain, and that would also possibly maintain it sequentially. First complete the single source at V1, then at V2 and so on. We want to do something which simulates it parallelly. There is no parallel algorithms here. We are just going to think about it that it does it parallelly, right? Okay. So we will now state exactly how the algorithm is going to proceed. Okay, so to begin with, let me ask, what is a possible estimate for the shortest path distance between every pair? So you want an estimate to begin with. So for every pair, what is the best estimate that you can give without doing much work? It is simply the edge between them if it is present. If it is not present, infinity, right? So that is the first cut in initial estimate, and we want to refine our estimate by improving it and finally settling at the value of the shortest path distance, right? So what we will maintain is, we will maintain this array, and this is an n squared sized array. For every xy, we will have the following things associated with it. So pxy will have pxy dot weight, which stores the current estimate of the shortest path from x to y. This will be initialized to be the weight of the edge if the edge xy is present. If the edge is not present, this will be initialized to infinity, right? Then it will store pxy x comma y dot first. As I described to you, we also want one shortest path from x to y as an output. Therefore, we will also store the first vertex on this path, which is not x, right? The first vertex is typically x, but from x to y, what is the next vertex? But it's called first in the paper, so I'll just use that terminology. And then pxy dot heap pointer, which says that for this pair xy, if there is a path in the heap, so we are going to maintain a heap of paths, and heap which is a priority queue, and we will also store the pointer to that path in the heap, right? So however your implementation of heap is, do not worry about what is the implementation. It could be an array based implementation, it could be a pointer based implementation, and so on. So we are going to maintain a heap, and let me recall what is a heap. So heap is a data structure which allows us to store certain entities with a key associated with it. And what do you think is going to be the key associated with paths? The weight, right? So we are going to have a heap H of paths with weight of the path as key, and what all operations does this heap support? Since you are aware of what is a heap, let me just write down that there is something called as extract min, that is, give me the path or an element in the heap. In this case, it is going to be a path of the minimum key value, right? And if it is a n element heap, it actually takes order log n to implement this. Although just viewing the minimum element is constant time, if you want to extract it, you still have to do work which is order log n if it is an n element heap, right? And I think what you are talking about so there is of course this insert should be supported, otherwise how will you even build this heap? So insert an element is also supported in log n time, and we will also assume that there is something called as a decrease key, which I think you are referring to as update, which can be again supported in log n time, right? And this is a min heap. So in a symmetric way, why wouldn't an increase key be supported? I mean, one would also want to possibly increase the key, not necessarily in Dijkstra's algorithm, but if you talk about a heap or a data structure, then why doesn't an increase key operation, why isn't it supported? So what is the purpose of keeping the elements in the heap? What is it that we want to do efficiently? Sorry? Find the minimum value, right? So let us say that, okay, currently my values, I'll just deal with integers. So currently my values are 14, 28. I'll not draw the heap, but I will just say that, okay, it is 14, 28. And this is an element 1, element 2, element 3. These can be paths or something else. This is 35, this is 16, E4, and how they are arranged in the heap I will let it for you to think about. You know about how it is arranged in the heap, but now currently the minimum element is 14, right, and this can be accessed easily. Now I am supporting something called as a decrease key. So let us say that I decrease the key of the element E3 and it becomes say 26, right, this decrease key makes it to 26. This is supported. What I am asking is, why doesn't it allow 35 to be made to 40? Still we will be extracting the minimum element. What if you increase the key of the minimum element? Yeah, so you are on the right lines. So one should think about it, that why isn't an increase key of the data kind of this thing supported by a heap, right? You are on the right lines, that we are interested. So if at least for all the other elements, if I do something, I do not have to change the minimum if this happens. But let's ask what happens if I change the change this value to 14 to something larger, right? So this is something that one should think about. Please think about this question, that why isn't an increase key supported? Will it be supported in a different type of heap, or can it be supported using the given operations, right? Okay, so this is out of the context, but okay, so we will assume that this decrease key is supported, and this decrease key is again supported. This is what you are calling as update, is supported in order log n time. But for this operation, remember that a heap doesn't support a search operation, right? It doesn't support efficiently search, and that is why we are keeping a pointer to the path in the heap, and this pointer allows us to efficiently access that path, change its key value, which is by the decrease key. Possibly the path goes up in the heap in terms of the minimum value, it may become the next minimum, and then we update the pointer accordingly, right? So this is why this pointer to the heap is kept. Okay, good. So we have the data structures in place. We have for every path pxy, the weight, the first element, the heap pointer, and this is the heap supports these operations, extract, min, decrease key in order log n time. Okay, so how does the algorithm go? It simply says that so it starts with initializing the heap, and what would you expect it to initialize the heap with? For every pair, we are going to insert one path into the heap, which is the candidate shortest path, and as we said, the initial estimate is just the edge weight if there is an edge. If there is no such edge, then we just have an initial estimate of infinity, right? So we say that initialize heap for every pair xy belonging to V, add the edge xy if it exists to H, and appropriately modify pxy. So I will not write each of these, but what does it say? Pxy, you have to change the weight, you have to change the first, and you have to change, there is nothing to change in the first is actually going to be y, because that is the next vertex on that path, and it is y, and the heap pointer is appropriately initialized. So that is what we do for every pair xy, right? And what we are going to say is, now this is the clever part of the algorithm, is while H is not empty, and you must have seen this template of the algorithms, right? At least in Dijkstra's algorithm, you must have seen that repeatedly it extracts paths from the heaps and does something, right? So similarly, we are also going to do the same. So while H is not empty, what should you do? You should pull out the first path from the heap, right? And in our case, what will be the first path that we extract? It is in fact our selected edge that we already agreed, that all of us agreed that it is going to be in the E star, or it is going to be an optimal edge. So the first time we extract an edge, we actually extract an optimal path, right? Okay, this should not hold every time, right? Because we have already inserted into the heap several other edges which are not optimal edges, not necessarily optimal edges. So yeah, so we are going to take out paths and we are going to process them in a particular way. So while the heap is not empty, or I'll just also add this, or the top element is not equal to infinity. Yeah, so as soon as the top element has become infinity, there is nothing to do because there are no more things, no more paths to process, so we can stop the process. Remember that between every pair there need not be a path. So initially our distance estimate should be initialized to infinity, and we are going to refine them as we go along, right? So remove, the first step is remove the top path. Let's call this path u to v from h. Now my claim is that this path can be of two different types in a generic setting. What are the two different types that come to your mind? Yes? Yeah, you had, sorry? Optimal or not optimal? This is one kind of classification that comes to your mind, and this could happen, right? We are going to claim a stronger thing, that what we are going to say is that whenever you take out a path from the heap, and if it is the first time you are seeing it between the pair uv, then it better be an optimal path. That is what we are going to claim, which is a strong statement, right? We are saying that if it is the first time, so remember at beginning you can say that for every pair I have not yet seen any path, because that is what you have done, and now the first time you see a path from the pair u from u to v, it is going to be the optimal path. We have to prove this. But this is certainly true for the first edge, right? The first edge we pick out, if it is from A to B, it is the optimal edge from A to B, right? So we remove this path, but now that classification that and because this fact that whether it is an optimal edge, optimal path or not is something that this algorithm cannot immediately tell here. It can be proved, but it cannot distinguish between that case here. So I cannot say if it is an optimal path, do something. If it is not an optimal path, do something. I have to look at the structure of the path and say something else, right? So I will just make a very simple classification. Is this path a single edge or is this path a non-trivial path? That is very easy to identify from the path itself, because we have already stored what is first. If first happens to be the endpoint, then it is a single edge. If not, it is a non-trivial path, right? So I will just distinguish between two cases. If uv is an edge, then I will claim that add uv to, and this is the claim. I mean, I am not asking is it an optimal path. I am saying that I will prove to you that this is an optimal edge. If uv is an edge, add uv to, okay, so I have not defined this ev star. So so these are the data structures that we maintained. We have one more additional data structure. So for every vertex we are going to store for that vertex the incoming edges that are optimal edges that our algorithm has discovered. So to begin with, this set will be called as EV star, right? So what does EV star say? EV star is the set of edges which are optimal edges which are incoming into V, which our algorithm will discover in the course of its execution. And so to begin with, what should EV star be initialized to? Empty, because we do not have any optimal edge discovered, and as we go along we are going to discover these optimal edges and populate this EV star, right? So we initialize this, so somewhere I should say initialize EV star to empty for all V, right? So this is one initialization step, and my claim is that if I discover an edge uv, I will claim that it is an optimal edge. I will prove this and I will already add it to EV star, right? And then what I will do is what exactly Dijkstra's algorithm does. For every w belonging to the vertex set V, I will do what we wrote as relax, but I will just write this as update uvw, and I will write this procedure update, right? So this update is very simple. It just says that it has identified this edge uv. We have claimed that this is an optimal edge. Now for every w, it is going to simply look at the current. I mean, for every w there need not be an edge. Maybe you currently have some estimate in pvw. We are going to check whether UV plus VW estimate is better than the current estimate. If it is better, then update that estimate. When I say update that estimate, you will change the weight, you will change the first. What will you change the first to? In this case, if I do an update to V, because V is now going to be the immediate vertex on the path, and then appropriately I will change the heap pointer, right. So this is what update does. We can write down the update exact details, but that is not very important. All of us understand what update does, right. So now what case is left? If UV is an edge, we have told how to process it. What is the case that is left? If UV is not an edge, that is, it is a non-trivial path, right. So if UV is not an edge, so actually this will happen irrespective of whether it is an edge or not. So that is it. We will not go into this. We will not check if UV is not an edge. This will happen irrespective of whether it is an edge or whether it is a path. For the edges, we have processed things separately. For the rest of the things, for every other path. So what we will do is, for all T such that TU belongs to EU star, you want to do update TUV, right. So at some point, if you have aggregated some edges in EU star, then you look at all the incoming edges and say that I will go do update TUV. Again, what is update TUV? You look at this estimate T, the weight of the edge TU plus the path estimate for U to V. If it is better than T to V, current estimate, you update it, else you leave it as it is. Again, what would be the first on such an update? It will be set to U. Is this correct? Because you are adding one edge. Any questions about this? So I will reiterate what is the algorithm. We are going to start with an estimate for every pair. For every pair, the weight of the path is set to the weight of the edge, the estimated shortest path weight. The first is set to the endpoint of that edge. The heap pointer is appropriately initialized, and for all the pairs where the edge is not present, this weight is set to infinity, right. And the EV stars of all vertices have been initialized to empty to begin with, and we are going to now repeatedly pull out paths from the heap. The paths could be trivial paths which are edges, the paths could be non-trivial paths. If the path is a trivial path which is an edge, we are going to additionally do something, because remember, for an edge also this applies, right. The third point applies for an edge also. If it is an edge, we are going to say that add UV to EV star, which is correct in the sense if we prove that in fact it is a optimal edge. And then for every W, we are going to relax or what is this update procedure. So how many of you would like me to write down the update procedure explicitly? It's not too much work, but I hope everybody understands what is update. So I will leave it. If you want, I can write it down at the end of the lecture. Okay, good. So this is the algorithm, and we would like to analyze and argue that this is a correct algorithm first before we show that this is an efficient algorithm, because at least this correctness ensured is something which is critical to any algorithm, right. Okay. So what seems to be the difficulty in proving correctness, or do you what seems what is the risk in this algorithm? So it seems that there are some paths that we may have never considered, which Dijkstra's algorithm may consider, and we may miss out some shortest paths, right. That is the only thing. If we are sure that every path is considered, then it will certainly compute the shortest paths. But we may actually not have looked at all paths, and if we miss out some path which is a shortest path, then we are in trouble. We may not get the shortest path for a pair, right. So and then we should also justify this step, right. Why did we suddenly take this edge and put it into EV star, where we don't know yet that this is an optimal edge? For the first edge this is true, but in general we would like to claim that this is true, right. So we will now establish a proof which is based on the invariants of this algorithm.